the impulse momentum theorem really told us this here. It says that if P1 equals J external equals P2, then what we said here is that if J external is not equal to 0, then P1 is not equal to P2. In other words, this causes, there's a change in momentum. But what happens here if it is equal to 0? If it is, then what we find is that the momentum before and afterwards, we then say momentum is conserved. And that's where we're at right now. This is where we're at. Now we want to talk about dynamic equilibrium. And in dynamic equilibrium, when we look at that, we say dynamic equilibrium and the total momentum of the system. And this is what we've been after the whole time. So what we want to do here is that we want to go in and we want to look at this thing. So what we want to do here is that I want to consider a system, a closed system. So consider a closed system of moving particles. Like what would be a closed system of moving particles? Imagine that you have a van full of kids, let's say 5 kids. The van's moving and there's no external forces acting on that van. But these kids may be in the van and having various collisions. So we don't look at how the kids are actually jumping around and colliding with each other. What we do here is that if we want to describe the motion of the van, what do we want to do? We want to focus on the center of mass location, because that's what momentum's about. So you could imagine here's my van. Right? And inside my van, what am I seeing? Well, I have the kids with various collisions, right? One's going this way, one's going that way. And we could all just be going like, what's going on? So when I look at the van, the key to all of this here is going to be this very special point, right? The center of mass location. So even though the car is moving, to describe the behavior of this system, we need to talk about center of mass. So here we go. So remember, V center of mass is going to be what? It's M1 V1. However many particles are in the system, divided by the total mass of the system. Now I can rewrite this thing here. And the way I can rewrite this here is that the term in the denominator is the total mass. So if I do a rewrite, then what I say here is that the total momentum of the system is then going to be the total mass times V center of mass, which is, of course, M1 V1, Mn Vn. This is the total momentum of the system. So I'm going to box this. No, I won't, not yet. And so here we go. If a system is in dynamic equilibrium, the external force, you know what, this is a little bit too tight for me. Let me move this just a little bit. The external force acting on the system must be zero. So this implies then, what does Newton's second law tell us? Newton's second law tells us that the external force must be equal to what? The derivative of this thing. But now we're talking about a system. So this is the total momentum that I'm looking at. But if that external force is zero, then what this tells us here is that the total momentum of the system is a constant of the motion. In other words, P total, which is equal to M1 V1 plus however many particles you have, must be a constant. No matter what. This statement is the statement of conservation of linear momentum. And it's a very, very powerful law. Okay? So I can write this a couple of ways, and I'll show you how people typically write it here. They'll say, okay, the total momentum, and here's how I write it. The total momentum initially equals the total momentum afterwards, which then I could come in here and rewrite this as the individual momentums beforehand must equal the individual momentums afterwards. Now remember what I said before. The momentum of the individual particles in the system must redistribute. Oh man, I don't know if I'm spelling this right. Redistribute their momentums or adjust after the collision such that it conserves V center of mass, which is proportional, of course, to the total momentum of the system. Right? Look at that. The system must redistribute their momentums. Right? This is the key phrase here. So what I want to do here is that I want to show you an applet. Okay? I want to show you what is known as a PhET applet. Applet for one-dimensional collisions. And I'm going to bring this back again later on, but I want to make sure that you see what I'm seeing here. So check this out. So what I need to do here is that I need to go into this guy. I'm assuming that you're seeing my screen. And what you're seeing here is that I have the velocities. Now, what you see here is that I have this, I don't know, magenta. I don't know what color this is. Is this fuchsia? I have no idea. I really don't care either. You could see that I gave them the same mass right here. And I gave them the same x velocities. So what they have here is that they have equal and opposite velocities. So before the collision, look where the center of mass is at. It's right there in the middle. It doesn't move. Right? So it doesn't move. The center of mass does not move before and after the collision. Now, what I'm going to do here is that this guy better not move because these guys have equal masses and the center of mass should be fixed. So look what happens. I'm going to run it. And as I run it, you can see that even afterwards, they have the same, that the center of mass does not move. So the before and after collisions tell us that that's not changing here. Now, what I want to do here is that I want to come in and I want to look at this thing this time for different masses and different speeds here. Okay, let me grab these images so that I could share them on my screen with you so that we can look at this thing here. Okay, I'm almost there. Give me just a moment. So now let's go look at this other scenario here. So what I'm going to do here is I'm going to return the balls. Now look what I'm going to do. What I'm going to do here is that I'm going to make one of the speeds faster. Okay, so let's come up here. Let's look at this guy here. And this time I'm going to enter 1. So it's now moving faster here. Now let's look at what happens to that center of mass of motion here. So if I click on this thing, see how it's moving? Look how it continues to move afterwards. Right? So what you're seeing here is that this velocity of center of mass here is moving. So even though the collision has occurred and these guys are already moving in a different direction, you're seeing that that thing continues to move in that direction right there. That's what I mean about the momentums of the individual particles must rearrange themselves in order to conserve velocity center of mass, or we could say then that it's the velocity or the total momentum of the system here. So let me go bring this into my OneNote so that I could make more sense of this thing here. So by the way, I can do the exact same thing with masses. I just did it with speeds. So here, let me go share my screen with you so you could see what I'm talking about. So here's my OneNote. So in this case here, what I really should be doing is I should be doing this, that this guy is the situation where now M1, M2 are the same, V1 and V2 are the same. But note, these are speeds, not velocities. Okay? Now the same thing happens on this case here. And in this case, What I'm seeing here is that I'm seeing this guy. What I'm seeing here is that this is not true in this situation where I do have the masses the same, but V1 is greater than V2. Again, we're talking about speeds. So when I look at V center of mass here, V center of mass is 0 before, V center of mass afterwards is 0. So this is before, and this is after the collision. V center of mass does not change. That is not true here, because this is before, this is after now, and what you see before here is that V center of mass is moving in this direction, and even after the collision, it's still moving in this direction. And the reason why this all happens is because why? This is my system. So my system is ball number 1 plus ball number 2. And what we say here is that F external is 0 or J external is 0. So this implies no momentums, no total momentum does not change. And if it doesn't change, then that's what I mean by this here, right? They must redistribute their momentums. They must change their speeds or their momentum values with mass times velocity in order to conserve V center of mass. That is a powerful statement. And dynamic equilibrium for a system has a parameter called the total momentum of the system. And we started looking at a closed system that had moving particles. And I said, imagine that we have a bunch of kids in a van that are going through various collisions. And we can define the center of mass motion. Since all of these collisions are internal to the system, they don't affect the velocity of the center of mass. And as a consequence of this thing here, that means the velocity of center of mass before and after will not change. And so related to the velocity of center of mass is this thing called the total momentum, which we can then write in terms of the velocity of the center of mass. And so if there's no external forces acting on that system, then that means here that there shouldn't be, shouldn't change it. So when I look at the total momentum of the system here, you could see that it's going to be a constant. And what I said here is that conservation of total momentum is one of the most fundamental laws in all of science. And what it says here is that when I look at the total momentum being a constant of the motion, that the total momentum before and afterwards, that the momentums of the individual particles must redistribute, rearrange their momentums in order for the velocity of center of mass to be a constant. Okay, that is super, super fundamental. And what we did here is that we looked at that applet. And if I had the same mass, the same speeds, then V center of mass won't change. But if I had different speeds or different masses, the center of mass continued to move in a particular direction here. And what I did here is that I went in and I showed you with the applet here. And if I come in here, look at the applet. So in this case here, when I look at the center of mass, well, this guy has a bigger mass, but it has a smaller speed. This guy has a smaller mass, but it has a higher speed. But when you're looking at this picture over here, the momentum diagram here, you could see that the momentum of 2 is bigger than the momentum of 1 when you multiply it out. So what you find here is that the total momentum is going to continue going to the right. And that's what that X is showing you here. So if I look at this thing, look how it's moving. It's moving very slowly to the left. Even after the collision, these guys are moving. Now, the thing that's interesting, you may have noticed that one is moving faster than two. And what you'll find here is that there's an exchange of momentums. And the crazy thing about this is that it literally is an exchange, but it's hard to see because of the masses here.